In this video, I'm going to walk through some assembly code that I am using to control the LCD that I've added to my 286 system. Maybe I'll start out with looking at just the schematic as a reminder. In the last video, I went through the actual connection of this. I talked about how I was doing the address decoding. If you're interested in any of that, go take a look at the last video. But essentially, on this LCD now, I have 8 data lines that I need to work with, and then there's 3 different control lines, an RS, an RW, and an E. And I would encourage you, if you're going to work with these LCDs, to go find the data sheet for the controller that typically is on the back of these LCDs. And I'm using this data sheet here. It's a Hitachi HD 44780. And it will give me details on what are the different lines, basically signals for that controller for the LCD, and how to use them. So for example, I've got this RS signal. It's basically a register select. I've got a read write, and then I have a start, basically a way to toggle start of a data read write. Then I've got some data lines, some power, ground, things like that, VCC, ground, etc. And it gives some good detail on using this LCD. I'm not going to go through this in detail here. If you're interested, take a look at that. But this is how I have it connected. I have 8 data lines connected to the port A of my PPI number 1. There is a way to do it with only 4 data lines. They call that 4-bit mode. I am using this 8-bit mode, so 8 data lines. And then I have my 3 control lines down here that are running into the first 3 bits of port B. Now with that, let me take a look at the assembly. And so this assembly, I think, is a couple hundred lines long. I put in some commentary in it right away just to remind me of how I need to work with this. For me to talk to that LCD, I want to actually communicate through PPI number 1. Now to work with that PPI, I have to use the address that I'm decoding for. And again, in the last video, I show that logic inside of my PSOC where I'm doing my address decoding for this system. And I've set it up so that E0 is the address that I'm going to use for PPI number 1. So I need to work with PPI number 1 through this E0 address to get to the LCD. And here is what it's going to decode. It's these first 5 bits is what I'm looking for. If it's a 11100, and this is within the IO address space, not the main memory. I'm not doing a memory mapped. I'm doing an IO mapping here. Because on the 286 there's a separate 64K memory address just for special IO where I can use a limited number of operations, or basically instructions that the processor supports, like in and out. And those to assembly, which you'll see those later, allow me just to use a special 64K range. And within that, I'm saying that E0 is going to be for PPI number 1. And then the next 2 bits I am mapping basically on the chip itself. It's going to have a pin labeled A0. It's going to have another pin labeled A1. I'm bringing in from the bus on my system address A2 into pin A1. And from the bus, I'm pulling address A1 into pin A0. And this goes back to the 286 is looking for a double byte or a word, 2 bytes. And the lowest value in this is actually how it selects the high byte or the low byte. And in my case, we don't want to use that. We're going to use this first 5 for the decode, and then the next 2, I'm going to be able to set, depending on how I set A2 and A1, so that I can access port A, port B, port C, or the control register. And so if those 2 lines are set to 0, 0, in other words, A2 is a 0 and A1 is a 0, I can now talk to port A. If it's a 0, 1, port B, 1, 0, port C, and a 1, 1 is the control register. And what that equates to in binary is it looks like this. And here's the hex values that equate to that. And so then I just set up little friendly labels so that I can say PPI1 port A, and I know it's going to go back to this E0, which is the address for port A. And then E2 is port B, E4 is port C, E6 is this control port. So if I want to change how this PPI behaves, I'm going to have to write stuff to this E6. If I want to read write whatever it might be to port A, I need to read write to E0, etc. I also set up 2 additional configurations here. When I actually go to set a configuration on the PPI, and you'll want to pull up, if you're going to work with this, pull up the datasheet for a PPI, but it'll give you the details of what are all of the bits that you can set and what does it change basically. So I'm going to have to write to this control register a value, and that value is going to do certain things. Now in this case, I'm going to tell it that I want to use IO mode and what's called mode 0, which is probably what you're going to use almost all of the time, and that my A port I'm going to use as an input. My C port I don't care about, but they split it in 2 halves, an upper and a lower 4, a nibble I suppose we could call that, a half byte, but 4 bits and 4 bits. I'm not going to use it, but I'm setting it as output. And then I'm also maybe to pay attention to my B I'm setting as output. So A is input, B is output. That's the biggest thing to pay attention to here. Then I have another configuration that is A is output instead of input, and B is still output. So B is output. Let me go back and show you B. Here's B. That was the control. So I'm going to treat that as output all the time. But then port A, I'm going to sometimes use it as an input and sometimes use it as an output. As an output, I'm going to write to the LCD, for example, a character, a value of a character I want to display. If I want to treat this as an input, that means I'm going to read from the LCD, and I'm going to do that to check the status and to see if the LCD is busy or not. I've also set up these down here. RS, I'm just saying, is on pin 1, RW is on pin 2, E is on pin 3, and that should match what I've got going on over here. So here's my 1 pin. You can see that that is my RS, then I have my RW, and then I have my E. So that's a way that I don't have to try to remember pin numbers. I've just got a friendly label. I can say RS, RW, or E. So then as I continue down through this, I do things like set up my register, disable interrupts, whatever there. But then I get to a procedure called LCD init. And I call it, and let me jump down to LCD init. In the data sheet for the LCD controller, I can go look up what are the things that I can send to it for commands, and what do those different things do. And I'm not going to go through all the choices, but I'll show you what I'm doing here. So I'm going to send this value, a hex 38, and that is going to tell the LCD that I'm going to use it in 8-bit mode. I'm going to use 8 data lines to communicate with it instead of 4. I'm going to expect to have the output on the screen be 2 lines of a 5x7 font. And so I load this into a lower A register, and then I write basically that register to the LCD. And you can see down here what that code looks like to write it. But basically I'm just going to go out and say, take this value and write it out. And I'm going to write that value out to the A register, and you can see that back over here, that when I write, I'm going to find what's the value that I put up above for port A, and then I'm going to go ahead and output to DX, which DX is the value that is port A. So to that address, I'm going to write AL, and AL is this value I had set up here. And then I have to toggle some bits. So I have to turn this E bit on and E bit off. And that toggle then basically says, okay, take that as a command and process it. So in this first case, I'm going to say, these are the things I want to set with this value. Okay, write that out to the LCD. Then I'm going to do a different set of settings, and that's going to say, turn the LCD on, turn the cursor on, and I don't want the cursor to blink. Write that to the configuration of the LCD. Then I'm going to clear the LCD, and then I'm going to basically increment and shift the cursor, and don't shift the display. The display, you can have it shift. I'm not doing that. I'm just going to say get that cursor in the first spot basically. So that's all part of the initialization of the LCD. After I initialize it, then I call a procedure called print message, and that just simply moves an H into my lower A register, and then calls a procedure to write that data to the LCD. So I've got a command write and a data write, and the data write basically says, you know, okay, go get me the address for port A, put it into the D register, and then take whatever value is in the lower A, which would have been in my case here an H, and then take that H, toggle this E on. Well, first write out that H to port A, and then toggle this E on, and then E off down here. And I just kind of put little reminders over here of how these are being set as I go through this. So R and E, and down here just RS. So RSE, RS on, E on. Down here I do just RS, which means E is off. So I'm going to say, here's the data of the character I want the LCD to display, and then I toggle this E bit. And that E bit again is just right here, the one that I've got highlighted. So I put the value of my character out to the LCD, and I toggle an E bit. And that writes that character. And then I continue that process. And so that was an H. I then do an O, L, A, and a space. And that's all part of this print message. So print message gets wrapped up, and then I come back and I then send to into my A lower register this value, which is basically telling the LCD to move the cursor to the beginning of line 2, and I send that as a command to the LCD. Then I have another procedure, and that one is a print message 2, and I'm just learning and playing with this, so that's why I've got a couple different ways of doing it. This first one was pretty manual. Send an H, send an O, L, A. That was, you know, that's a lot of code. It's kind of verbose. The second one allows me just to basically point to a string, and so I've got a string down here further that says 8286 at 8 megahertz exclamation point. So that's the string, and basically I'm going to refer to it as this a string test. And if I come back up, then I'm going to basically get a pointer to that and then call this print message 2, and this basically just iterates through that. I had some help from someone on YouTube, so thank you again for your help on this. But this then iterates through that string and basically writes it out to the LCD. So I don't have to do individual calls like this. I just point it to a string that I've stored somewhere that is null terminated, and that will write it out. So now I have that procedure, and I finish calling it, and then that gets me to a halt. These other pushes and pops, I'm sure there's a much better way to do this, but this is just to help me to get my basically my data segment to be where my code segment is, so that when I call this code, it knows how to get to, or it can get to this this specific thing here, which is stored within my ROM space, not down in RAM. And that's one of the tricky things I found with the 286, is just learning how these segments work and all of that. So I'm still hacking my way through it. So as I'm going through this, if you catch anything that doesn't look right, let me know. Or if you see a better way, definitely let me know. Other things that I might call out as I go down through this, when I got to this print message, you know, I get down to, well, let me back up. I've got LCD init, and that called this command write. But something that was at the top of command write and also at the top of data write is a call to this other procedure called LCD wait. And what LCD wait does is actually goes out and checks the status of the LCD to see if it's busy. And if it is, it just sits in loops until the LCD is not busy. You'll see some code out there where they'll just put in manual loops or timing delays, things like that. Probably not the best way to do it. The way that you should work with these LCDs is to check the status of this busy flag and don't do anything with it until the busy flag is 0, saying that it's not busy. So what this procedure does basically is it checks that flag. It says, okay, I'm going to go out and I'm going to change my PPI port A to be input. And so going back here, port A input. In other words, I'm going to read from the LCD to the PPI. So I want to read from it, and then I toggle this E, and so I turn E off, I turn E on, and then I read in from the LCD into the PPI, and I rotate that value left 1 bit, and it's the highest bit, so bit 7 down to 0. Bit 7, if it's a 1, the LCD is busy. What this code is doing is it shifts that 1, I shouldn't say shift, it rotates it left, and if it rotated off the left side, in other words, it was already at bit 7 and you rotate left, it puts it into the carry flag. So I can then say jump if the carry flag is set. Really what this is doing is just saying look at the highest bit, the 128 value bit of that byte that it read from the LCD, and if it's set, the LCD is busy, then jump up here and just repeat this process, and just repeat, repeat, repeat. And at some point the LCD will say, okay, I'm not busy, and then we'll continue on, and I'll put the PPI into output for port A. So I flipped it to input, now I flip it back to output. So this is just a nice, I think, the proper way to work on a system that can run way faster than that LCD could ever keep up with, and not cause the LCD to have issues. Now let me comment this code. I think I put a note up here somewhere. I found some samples of that code in this book. I just put the beginning of the title. It's the 8086 IBM PC and compatible computers, and it's got a lot more to the title, but 4th edition by I'm going to say Mazzidi and Mazzidi. That's probably incorrect, but that's my best shot there at pronunciation. But that had some sample code in it, and I've also done some of this with Ben Eater's 6502 in the past, and I've worked with these LCDs a little bit. I did modify the code out of this book a little bit. They had maybe shortcutted some stuff that I expanded out, and I think that was mostly in the wait procedure. They were not in the loop toggling the E bit every time. And if I look at the data sheet, I kind of think you're supposed to be toggling that. And then I see what the data sheet is. I can go find a page like this, and it talks about this busy flag check and what the timing diagram looks like for that, and how I can keep checking that DB7, that highest data bit, and see if it's busy. Is it busy? Is it busy? But what they're showing here is that E is being toggled every time, and the code in that book did not do that, so I modified it so it did toggle it every time. And then I guess I've got a delay procedure that I'm not even using, I don't think. It's just in here. And that's about it for this code. So this code seems to be working well. If any of you see something here that you would suggest I change, let me know. But with that, let me show you it running here. And I start out with the system off, and then I'm going to turn it on, and you're going to see that LCD comes up instantly. Just a real quick note, I have the processor running at a full internal P clock or processor clock of 8 megahertz at this point. So I'm running an oscillator up on my clock card that is a 32 megahertz oscillator. On my clock card, I go through a flip-flop on the way out, just so I have a really nice clean clock signal. That cuts that 32 down to 16. It cuts it in half. So that's a 16 megahertz clock that's going into the processor. And then the processor internally uses half of that for its clock speed for the processor internally. So that's an 8 megahertz. So I am running a full 8 megahertz processor in this configuration, and it is running well. And I'll just let this video loop here. But to make that happen, I did have to do maybe a few things. When I initially got this LCD up and working, I was just running a low speed, like on this 555, like you see in the video where I switch it over, and you can see the LEDs moving through things. That's because I'm running at whatever the fastest my 555 timer can run at. which is down in the kilohertz. What did I say? It was 2 kilohertz, maybe, if I recall correctly from a previous video. So it's not super fast. But the other part of this video, initially when I turned it on, I was using the full 8 megahertz, and you can tell because it pops up instantly and says Ola 8286 at 8 megahertz. But when I first got this code up and running, it was with the 555, the slower speed. I tried running a 1 megahertz CAN oscillator, and it would not run at that speed. So I cut it in half and cut it in half and cut it in half, and the fastest I could get to run at in the processor clock was down in the 32 kilohertz. So really not very fast at all. And that was a problem. So I was trying to figure out, well, what was causing that? Is it a code problem? Is it something in my circuit that I didn't have right? I did make a couple of changes to get it to run at 8 megahertz. One was on my PSOC. A couple of these pins have capacitors built on them on the PSOC. And as I was using my oscilloscope, I noticed one of them, specifically the signal going into it, just looked a little weird. And then as I looked at the PSOC a bit more, they note on the picture of it that, oh yeah, these pins have a capacitor attached to it. So I moved that signal input to a different pin that didn't have a capacitor, and that got my system running in the megahertzes quickly, very quickly. So that was the first thing I did. The second thing I did, at the very bottom of the bus board, I've now added in pull-up resistors on the address and data lines on the bus. And I'm just using a 1 kilo ohm resistor network, a SIP there, and I'm pulling that up to VCC. And so every one of my data lines and address lines between my latches and transceivers out to all of that stuff to the right has a 1K pull-up. And that, at that point, really the system's running well. It's nice and stable at 8 megahertz as far as the processor clock. And all the LCD code is running. I have no artificial delays or loops or wait states for the LCD other than checking for the busy flag, and it's working great. In the first build, I had some issues trying to get it to jump to the second line. I don't know why, but here, just everything I've sent to that LCD for commands, it just takes it, and it's running great. So that's where I'm at. Again, I'm pretty happy. This is a nice milestone that got the LCD working. I've got the PPIs working, or at least one of them at this point that I'm using. And the system's running at what I am very happy with as far as 8 megahertz in this kind of hybrid PCB breadboard and a whole lot of wiring. So I'm not going to complain about that. And I don't know if I need to try to take it any faster the way it sits right now, but so far this is coming together okay. So I think where that leaves me next is probably to get into this PPI number 2, try to get a PS2 keyboard input working. And to get that working, I need to get my interrupts working. And I think I've got some learning to do there for sure. So this chip right over here by the processor is my interrupt controller. I'm going to have to figure out how to use that. I've already done the address decoding for it, but I need to get it wired in. I need to figure out how to write the appropriate configuration to it. I need to figure out how to set up my interrupt vector table in code, actually set up the interrupt routine for a key press, read which key or scan code comes from the keyboard, turn it into something ASCII value-wise, and show it on the LCD screen. So that's going to take a whole lot of effort, and I can see all kinds of speed bumps as I try to work through that, but I'm going to try to do that next. So thanks for following along, and more to come.